This video discusses a variation on both the disk and washer method, and that is, well, what if the axis of revolution is not around the x-axis or the y-axis? And so let's do sort of a variation on the problem that we did in the previous video. Let's say that we have the same functions, y equals x, and here we have y equals x squared. But instead of revolving around the x-axis, let's say that we're revolving around the line y equals -2 down here. So in this case, we're going to use the exact same formula, which is the pi integral from a to b of r outer squared, that's a squared, not a slashy thing, minus r inner squared, parentheses, and then dx. The only difference is that the radius isn't just the function. The radius for the outer radius is going to be the y value here down to y equals -2. And so the way we calculate that is to just simply do x minus and then the y value of the axis of revolution, which is -2. So we'll have x minus -2, and then actually we can put the... So this value for the axis of revolution shows up here when you do a rotation that's not around the x-axis. And to be even clearer, you want to keep with the whole top minus bottom idea. So for example, if the axis of revolution is up here at like y equals 6, then the 6 would be first, and then you would subtract x in order to get that radius. So just keep in mind which function is on top, and then just do top minus bottom for that radius value. The inner radius will be x squared minus the -2, like this. Oops, close that -2. And then squared again. This squared still needs to stay there. And then you can put big parentheses around it, dx, and then your integral still goes from 0 to 1 pi. So oftentimes these questions are formulated as just write an integral representing this area. And so if that was the case, this would be your answer. And you can simplify if you want to, but you don't have to bother because, this shows me what you're thinking. It says, okay, here's your top function, here's that axis of revolution, here's that bottom function, here's your axis of revolution. We're squaring both to get the disk and then the inside disk, so we're using the washer method and then subtracting them, so we're good. So this is a good example here. Let's do another example where we're just trying to set up the integral. So let's say that we have this region, which is bound by the equation y equals the square root of x. Let's try to figure out this top equation. It's a straight line, clearly y equals 3, so this equation is y equals 3. And we're going to revolve this region around the line y equals 5. So this is going to be an example where the axis of integration is above, the axis of revolution is above the region. So if we imagine this red section, essentially we're going to end up subtracting a red cylinder that looks like this. And then if we draw in the blue region, kind of goes off the page a little bit, but you can imagine that we sort of have this, like, I don't know, like a trumpet-shaped thing pointing this way, or I don't know, something like that. But you can imagine practical applications where you have to make something that's three-dimensional and then drill out something and then figure out the volume of it. So this is an application of that. But let's write an equation for the volume of this. So we're going to have pi integral from a to b. Same idea. So r outer squared minus r inner squared. So the outer radius is still the blue radius, but now to figure this out, we're not going to use square root of x minus 5. What we need to use is 5, because that's the top value, minus square root of x. Okay? And so hopefully you see that that's clear, that we want to do top minus bottom. And so using that here, we would get 5 minus square root x close parentheses, squared, that's our outer, minus, and then for the inner radius, we want to use 5 and then 3 because that's the bottom equation. And so we're going to go from 5 minus 3. You can simplify that if you want to. I'm just going to leave it as 5 minus the red equation, which is 3 squared. Close all your parentheses, dx. And that's almost it. So notice again here, we see that there's this separate term that's added or subtracted, and this is from the axis of integration. And then for a and b, you just do the x values. So we started at x equals 0, and we ended at x equals 9. And so that would be an integral that represents the volume of this region rotated around the line y equals 5. Alright, let's mess things up a little bit and throw a dy integration in here. So let's say that we have this region, which is bound between the two functions y equals x cubed and y equals x. And in this case, we're going to revolve this around the vertical line x equals -1. So if you imagine this, we'll have, I didn't really draw this very well, but we'll have sort of this it'll be like a sort of an open bowl shape with a large hole in the middle. And so to do the volume of this, we use the same idea where we want to do the r outer squared minus r inner squared. So our volume will be the integral. The limits go from 0, the y equals 0, up to here. This intersection is 1, 1, so our top limit is y equals 1. The outer radius here, notice that it's no longer the top function, but it's the rightmost function. And so the rightmost function is y equals x cubed, but because this is a dy integration, I need to solve for x in terms of y. So we need to rewrite this equation as x equals the cube root of y, or let's write it as y to the 1/3, because that'll make it easier to integrate if we have to. So our outer radius will be y to the 1/3, and then minus, there's that axis of revolution, which is at -1 squared, and then we're going to subtract the inner radius, which goes from here, which is y equals x, so rewriting x equals y, down to -1. So it's going to be x minus, and then parentheses, -1, close parentheses there, squared, and then we can close the black parentheses before the dy. So again, here you're basically following the same format of our outer squared minus our inner squared for using washer method in various forms. Again, here challenging problems where the axis of revolution is not the x or y axis. So that's how you do those. Enjoy.